This webcast continues in Worksheet 1D. Now we're going to look at some examples where the scatter plot that shows the relationship between our variables is not linear, because in the real world, not every relationship between two variables is linear. Okay, so let's look at number 3. And here we have a scatter plot which is showing us accidents versus age. And so as age increases, the number of accidents also increases, but it doesn't do so in a linear fashion. Let me just begin by maybe sketching in the shape of this trend. And I can see that it's curved. It is not linear. And there are really many ways to be curved, right? There are parabolic functions, exponential functions, inverse functions, and many other types. And if you don't recognize this shape and what type of parent function that belongs to, you can always go back and look at the reading on linear models, which you've already read, and at the end of that reading, it has a table which gives us the shape of graph, and over on the right it shows an algebraic expression, a mathematical equation that represents the shape of that graph. And so by going by the shape, I can go down this table until I see something that seems similar to the data. And I'm looking here in the bottom row, right here, the shape of this, wait a minute, let me go back and look again just to make sure. Yes, okay, so this graph seems to have a similar shape to the data that we have on how accidents depend on age. This is a graph which says that the y variable, that's the dependent variable, is proportional to the square root of x. And an equation for that would be y equals some slope times the square root of x plus the y-intercept. Okay, so that's what this looks like. So it looks like that accidents are proportional to the square root of age. In other words, y equal some slope times the square root of x. That's what that function looks like. And so if we wanted to make this graph be linear, now we're not changing the type of relationship, but what we're saying is that in order to make this linear, remember that a line has the equation y equal mx plus b. I need to make this x be the square root of x. Then I've not fundamentally changed the data. I mean, I'm not altering it, but I'm just trying to transform it in a consistent way so that when I graph it, it will be linear. Then I can find a slope and write an equation for it. And so I want to graph accidents versus the square root of age. So I would take a table, and accidents would not change. I would leave that data alone, but I would take the square root of age. And so I would calculate the square roots of the age and then redo my graph, and I would get a line, probably. Okay, let's look at another example. Number 4. Now here we have data that's showing how the orbital period, that's the time that it takes a planet to orbit all the way around the sun, to make one full trip around the sun, how that period depends on the radius of the orbit. Okay, and if you look at this, this also is not a linear trend. It has this kind of curved shape. And so, let's see, so what would we try first to linearize this relationship? Well, let me go back to that reading on linear models, and I think this looks to be the closest match to the shape of our data. And that's a situation where y is proportional to the square of x. Not the square root, but the square, right? X squared. So the mathematical equation for this type of function would be y equal some slope times x squared plus the y-intercept. Okay. So to linearize this, we would try to graph period versus radius squared, right? And we're basing that because this graph looks like a curve, a function where y equals some slope times x squared. And so I'm going to square my x, which in this case is the orbital radius. I'm going to square the orbital radius. So actually, this relationship and this data is well known, and this did not work. Squaring the orbital radius did not result in a linear graph. And that happens sometimes. I mean, you go by the shape of the graph and you say, well, it looks like this. And so that tells you what to try. But in this particular case, it's a famous example, and several tries were needed to actually make the graph linear. Johann Kepler was the person who worked out this relationship in the early 1600s, and he did eventually get to a linear relationship. And in order to do that, look at this, he had to take the square of the orbital period versus the cube of the orbital radius. And so after he made that transformation, he did get a linear graph, and he was then able to write a physics equation for it. And so one question is, does the same equation apply to the graph above? Well, yes. You know, when you are linearizing the data, you are not changing the data. You're making a consistent transformation. So every data point for orbital radius got cubed, and every data point for orbital period got squared. So we have not altered the data or altered the relationship. We are just changing it in a way so that we can visualize the graph of the relationship as a line, and then we can write the equation of that line. So it would still match this data. If we took this same information and went back to period versus radius, it would still be curved in the identical way. We have not altered the data. So let's write the physics equation for this graph. They are telling me the slope, and they're telling me the y-intercept, so I don't have to find those. So first, to write a physics equation, we should come up with descriptive names for our variables. And so for orbital period is usually denoted as an uppercase T, because period is really the time that it takes a satellite to move a full revolution around, in this case, the sun, whatever's at the center of its orbit. And orbital radius is usually just called lowercase r, right? For radius. Okay. So in our case, for this graph, the dependent variable is the square of the orbital period. So orbital period is uppercase T, but we had to square it in order to get this line. And the independent variable is the orbital radius, but we had to cube it. So I need an exponent of 3 on that r in order to get this linear graph. So when I go to write the equation of this line, you know, the equation of the line is y equal mx plus b. Well, my y is t squared, right? And the slope, which I put in parentheses, is 0.9996. They gave that to me. What are the units of the slope? So I have to look at the graph, and on this graph, the units of the y-axis are years squared, and the units on the x-axis are AU squared. AU means astronomical unit. It's just one type of measure for length. So I have years squared over AU cubed. I don't really need to understand a lot about those units, but I'm just learning that when I'm putting the units on a slope is always the change in the y variable divided by the change in the x variable. So the units should be the units on the y-axis divided by the units on the x-axis. Okay, so I've got y equals m. Now I need to put in my x variable, which is the cube of orbital radius. And then I need to add my y-intercept. And in this case, the y-intercept is negative, so I'm adding a negative. So I'm just going to write negative 0.9, and the units of the y-axis should be years squared. So this is a good physics equation for that linearized data.